Welcome. In this video, we'll explore the concept of bus structure in computer systems. The bus structure is a fundamental aspect of how computers communicate internally, connecting various components like the CPU, memory, and input-output devices. Understanding the bus structure helps us grasp how data travels within a computer, ensuring efficient processing and communication. Throughout this video, we'll break down the main types of buses, their roles, and how they impact overall system performance. Let's begin our journey into the world of computer architecture by first understanding what a bus is and why it's so essential. Bus in computer architecture refers to a communication system that transfers data between different components of a computer. Think of it as a highway for information, allowing signals to move efficiently from one part of the system to another. Buses can carry data, addresses, and control signals, making them crucial for the operation of any digital system. By providing a shared pathway, buses help reduce the complexity of wiring and make it easier to expand or modify the system. Next, let's look at the main types of buses found in most computers. There are three primary types of buses in a typical computer system: the data bus, the address bus, and the control bus. Each serves a unique function. The data bus carries actual data between components, the address bus specifies where that data should go, and the control bus manages the timing and coordination of these operations. By dividing responsibilities, these buses ensure that information flows smoothly and accurately throughout the system. In the next scenes, we'll dive deeper into each type of bus and see how they work together. The data bus is responsible for transferring actual data between the CPU, memory, and other devices. Its width, measured in bits, determines how much data can be moved at once. For example, a 32-bit data bus can transfer 32 bits of data simultaneously, which directly affects the speed and performance of the computer. The wider the data bus, the more information can be processed in a single operation. Let's see how the data bus interacts with other buses in the system. The address bus carries information about where data should be sent or retrieved within the computer. It transmits memory addresses from the CPU to other components, ensuring that data is stored or accessed at the correct location. The width of the address bus determines the maximum amount of memory the system can address. For example, a 16-bit address bus can access 65,536 unique memory locations. This bus is essential for organizing and managing data storage efficiently. The control bus is in charge of sending control signals that coordinate and manage the activities of the computer's components. These signals include read and write commands, interrupt requests, and clock signals. The control bus ensures that all parts of the system work together harmoniously, preventing conflicts and errors during data transfer. Without the control bus, the system would lack the necessary coordination to function correctly. To better understand how buses connect different parts of a computer, let's visualize a typical bus structure. Imagine the CPU, memory, and I/O devices all linked by three main buses: data, address, and control. Each bus runs parallel to the others, forming a shared pathway for communication. This structure simplifies the design and expansion of computer systems, making it easier to add or upgrade components as needed. In systems with multiple devices, bus arbitration is necessary to control which device can use the bus at any given time. Arbitration ensures that only one device transmits data on the bus, preventing data collisions and ensuring orderly communication. There are several methods of bus arbitration, such as daisy chaining and centralized arbitration, each with its own advantages and trade-offs. Buses can be classified as synchronous or asynchronous based on how they coordinate data transfers. Synchronous buses use a common clock signal to synchronize communication, making data transfer predictable and efficient. Asynchronous buses, on the other hand, do not rely on a shared clock, allowing for more flexible timing but requiring additional control signals. Each approach has its own strengths and is chosen based on system requirements. The width of a bus, measured in bits, directly impacts the performance of a computer system. A wider bus can transfer more data in a single cycle, increasing overall speed. For example, upgrading from a 32-bit to 64-bit data bus doubles the amount of data that can be moved at once. However, wider buses may require more complex hardware and increased cost, so designers must balance performance with practicality. Bus speed, often measured in megahertz, determines how quickly data can be transferred. Faster buses enable quicker communication between components, reducing bottlenecks and improving system responsiveness. However, increasing bus speed can introduce challenges such as signal integrity and electromagnetic interference, which engineers must address through careful design and shielding. Bus topology refers to the physical or logical arrangement of bus connections in a system. The most common is the single shared bus, but other topologies like multiple buses or hierarchical buses are also used. Each topology has its own advantages in terms of scalability, cost, and performance, and the choice depends on the specific needs of the computer system. Over time, several bus standards have been developed to ensure compatibility and performance. Examples include PCI, PCI Express, USB, and ISA. Each standard defines the physical and electrical characteristics of the bus, as well as protocols for communication. These standards allow different devices and manufacturers to work together seamlessly. Bus protocols are sets of rules that govern how data is transmitted over the bus. They specify timing, data formats, error checking, and handshaking procedures. Proper protocols are essential for reliable communication and data integrity, especially in complex systems with multiple devices sharing the same bus. Bus contention occurs when two or more devices attempt to use the bus simultaneously, leading to conflicts and potential data corruption. To prevent this, systems use arbitration and control mechanisms that ensure only one device can access the bus at a time. Proper management of bus contention is vital for maintaining system stability and performance. Bus expansion allows users to add new devices or upgrade existing ones by providing additional bus slots or connectors. Expansion buses like PCI and USB make it easy to connect peripherals such as graphics cards, storage devices, and network adapters. This flexibility is a key advantage of bus-based computer architectures. In complex systems, buses are often organized into hierarchies, with primary and secondary buses handling different types of traffic. For example, a high-speed system bus connects the CPU and memory, while slower peripheral buses handle input-output devices. This hierarchical approach optimizes performance and resource allocation. Bus multiplexing is a technique where a single set of lines is used to carry different types of signals at different times. For example, the same lines might carry address information during one part of a cycle and data during another. Multiplexing reduces the number of physical connections needed, saving space and cost, but requires careful timing and control. Bus buffers and drivers are electronic components that strengthen signals and ensure reliable data transmission over long distances or multiple devices. Buffers prevent signal degradation, while drivers provide the necessary power to move signals across the bus. These components are essential for maintaining data integrity in large or complex systems. Bus errors can occur due to faulty hardware, poor connections, or timing issues. Common symptoms include data corruption, system crashes, or device malfunctions. Troubleshooting involves checking physical connections, testing components, and using diagnostic tools to identify and resolve issues. Proper maintenance ensures the bus system operates smoothly. To wrap up, the bus structure is a critical part of computer architecture, enabling communication between all major components. Understanding how buses work helps us appreciate the complexity and efficiency of modern computers. Whether it's data transfer, expansion, or troubleshooting, the bus structure plays a vital role in system performance and reliability. Thanks for joining us on this journey through the world of bus structures.